Ali.
Hello?
Um, okay, today I have a surprise for you, and I think you all been waiting for this interview for a while.
I hope not.
This is Dr. Andrew. Okay, I finally managed to get him and make him sit down and talk to me. So, Dr. Andrew Norton,
Yep.
and Dr. Andrew is a postdoc here, as you know. You all know, I think. Um, he's a postdoc in Stanford University, and he worked in the physics department with me, and he's doing very interesting research, which I already introduced to you a couple of two interviews I made, one with Vanessa, Dr. Vanessa, and one with Professor Bruce. Professor Bruce, he's supervisor.
Yes.
Supervisor. But he's actually working with Professor Stephen Chu, the Nobel laureate. His boss actually won a Nobel Prize. So I let Dr. Andrew welcome first, Dr. Andrew, and thank you very much really for coming and talk to me.
Sure.
And I let him introduce himself to you.
Yeah, hi. So, like Ahmed said, I'm a postdoc here at Stanford. Been here about a year and a half now. Primarily been working for Professor Bruce McIntosh in the physics department. And then also on a joint project with Professor Stephen Chu. And we primarily do research in a field called adaptive optics, which I believe Dr. Vanessa and Professor McIntosh had discussed or had mentioned. Um, and I've been here primarily just working in Bruce McIntosh's laboratory in the basement of the physics lab, building optical systems and algorithms and conducting research. Right now,
So I sorry to interrupt you.
sure.
Maybe you first tell us about your background.
Oh, yeah, okay.
What did you study in the past?
So I studied. I have a PhD in electrical engineering from UC Santa Cruz, and that's just over the mountains here, over towards the coast. And while at UC Santa Cruz, I did a lot of research in adaptive optics there. UC Santa Cruz houses the Center for Adaptive Optics, and it's kind of a research facility that is doing some exciting stuff in this field. And so my PhD is in electrical engineering from there.
So you're actually you're specialized in adaptive optics. This is your field, your research field.
Yeah, I guess it is the field that I know most about, and then like the electrical engineering, I think about it as like a tool set or ways of solving problems that we use when working on systems. So my research in graduate school was focused on an aspect of adaptive optics that had to do with the laser guide star, which will take some explaining, but essentially, let me start, I guess, with adaptive optics, and then it'll make sense what a guide star is. So adaptive optics is it's a relatively simple idea, and it's primarily concerned with the correcting of images that have been blurred by the atmospheric turbulence. And so when astronomers turn their ground-based telescopes and look at the night sky, the light that's been essentially propagating from the stars that they're looking at propagates through empty space, and then before it gets to the ground, before it gets to the telescope, it encounters the turbulent atmosphere of Earth.
That's right.
The very thing that, of course, that sustains our lives. It's a very dynamic source of aberrations in the sense that it's constantly moving, and there are pressure variations that get set up in the turbulence. And the pressure variations and the temperature variations essentially give rise to index of refraction variations. And if you remember from light propagating through different material, the index of refraction is kind of how fast or how slow the light slows down, or how fast it goes through a certain material.
So the index of refraction could be coming out of change because of like clouds or because of
It's not particularly clouds.
Mhm.
It's really just It's really just varying regions of different pressure. And in the visible and near infrared regions, from 400 nanometers out to like 2.5 microns, maybe 5 microns, the varying indices of refraction in the atmosphere give rise to different delays in the propagation time of the light through the atmosphere. So no clouds, just like right now, right? It's a very, very clear day. If it were nighttime, say there's no clouds around, and we were looking at our favorite star, we would still see, and this is again in the optical and infrared wavelengths, we would still see that star would appear blurred or distorted on our detector. Our image of it would not be very crisp. It wouldn't be very clear. So even though it's a clear night, there's no clouds. The atmosphere is extremely turbulent, just just the way that it's set up to move energy from these large scales to these small scales, and that gives rise to this convection that is kind of always present.
and how this then adaptive optics come into play or
So
help in this?
So the nature of the adaptive optics system is primarily concerned with measuring how the light is distorted when it gets to the bottom of the atmosphere, and then correcting for those distortions in the light before the atmosphere changes again, and that lets you produce a well-corrected what we call wavefronts, or that lets you produce really nice images looking through the atmosphere.
Yeah. So then
Maybe more about the mechanics of how it works.
yeah, that's what I would like to know. Like, it's not about the principle because the principle is kind of clear to me.
Okay.
That how you do the correction, but in terms of what do you use to create that kind of correction? What kind of instrument you use?
Yeah. So we use a device that's correctly labeled a deformable mirror. It is really just a mirror that does exactly that. It deforms. That is, the surface of the mirror changes its shape. And it can change its shape because you have a thin reflective coating that makes the mirror. But that thin reflective coating sits on these on these kind of pillars of actuators.
Okay.
And you can address each of those actuators electrostatically, typically, or magnetically. And that will deflect the post or the beam that the mirror is sitting on. And as that post deflects, it'll change the surface shape of the mirror. And a surface deformation, like a change in physical distance, relates to a change in optical distance, or delay of time, or delay of distance, or delay of phase. And the phase values of the electric field essentially govern the structure of the image. So if the phase values are all the same, that is, if they're all the same relative to each other, you bring that light to a focus, you have a really nice image. If the phase values are very different from each other across the light that you're looking, and you bring that to focus, you have a very blurry image. And so the deformable mirror adds it adds back these delays that the atmosphere has caused into the light.
And that's happening at the micro scale.
It's happening. It's happening at the micro scale. Typically, it's fascinating because, like for instance, Bruce is the PI on an instrument called the Gemini Planet Imager, and it's an adaptive optics system designed specifically for direct imaging of planets orbiting other stars. And that adaptive optics system is mounted to the back of a 8-meter telescope.
8 meters.
8 meters. Right.
Okay.
So it's like 24 feet in diameter.
And that all focused down to.
So that entire 24-foot diameter, that beam gets what we call demagnified or compressed, and then that fits all onto a deformable mirror, the device we were talking about. And that deformable mirror in Bruce's system, there's two of them, but the smallest one is
I believe it's
like an inch in diameter.
Yeah, something this size.
Yeah, it's like that. Right. Wow. So the whole 8-meter telescope gets compressed and put on that.
So 8 meters, it's a circle, I believe.
Yeah.
a circle with diameter of 8 meters that you compress the image or the light gathered by this big satellite or
Right.
dish into quarter inch or 1 inch.
Yeah.
There you go.
Yep. And then within that quarter inch area, there are about 4,000 little actuators, and they're each spaced about 300 microns apart, and they can push and pull in the mirror and deflect the surface of the mirror, and they can deflect the surface of the mirror about 3 to 4 microns.
So these are what they call MEMS. I know what
Yeah.
MEMS are, but can you give an idea how what is MEMS exactly?
Yeah, MEMS stands for micro electrical mechanical systems, and these are devices that are primarily built from the same kind of technology that integrated circuit technology is, with patterned and lithographed layers of silicon and dry etching or wet etching. And so you can deposit layers and then sacrificial layers and remove those layers with chemicals, and then you can essentially build the freestanding devices that can be electrostatically addressed.
So now let's look at, look at the number of people or professional or people who's doing different field can fit within this project. So you need someone with image processing experience,
Image processing.
image processing, and even someone with instrumentation experience
Sure.
for like embedded system or
Sure.
to integrate the MEMS with your chip,
Absolutely.
and you need someone who has experience with fabrication to fabricate for you the MEMS.
Yeah.
I know you can buy them from there, but the person is still
They're still
Okay.
helping you
Yeah,
towards your final goal.
he gets the education, right?
Yeah. Yeah.
So,
Absolutely.
so that's it. That's very interesting. So just one last question
Sure.
before we go to the next part of this conversation. It's still about the MEMS.
Yeah.
And you mentioned that part of the mirror, when it tilts, it actually causes some kind of glare. And
Yeah.
to my knowledge, the light comes to this coming from outside. It's like a almost plain wave front.
Right. It's like a wavefront, right? All the
And-
phase
and-
values are the same.
Yeah, and then
relative to each other.
is it because it's a really large wave front, okay, plain wave front? Does it this change? Very tiny changes, like a couple of microns
Yeah.
change. Does it cause that delay? Do you think? Is
The
it not-
atmosphere?
Yeah, for the image.
Yes, that's what the atmosphere imparts in terms of a delay in distance to light coming through it. So if you wanted to look at like a region across the 8-meter telescope, after the plane wave, all the phase values are the same relative to each other. If you looked at that after it propagated through the atmosphere and different regions got delayed and froze the time and looked at the light at that slice in time, the phase values would be slightly different from each other. And across an 8-meter telescope, the relative delays would be on the order of a few microns.
And that will be resulted in terms of like intensity variation of the image itself.
Of the image, when you bring it to focus, yeah. When you bring it to focus, you have a highly distorted image. The intensity, right?
So if I have intensity, let's say distortion at some point, I can correct that by changing the phase or the distance of these mirrors somehow, and add some kind of.
Right. Yeah. So that's absolutely right. You can essentially restore the intensity to what it should be if the atmosphere wasn't there with the adaptive optic system. The deformable mirror adds back in the correct delays of phase values of the electric field, or delays of distance, or also delays of time if you want to think of it like that. But there's also the other component of the adaptive optic system, which is the wavefront sensor, and the wavefront sensor it kind of sits just upstream, optically upstream from the deformable mirror, and it's looking at the deformations in the light as it's propagated after it's propagated through the atmosphere. So the wavefront sensor is reading out how the light is deformed, and then the control computer takes those signals, and
Yeah.
sends them to commands to the deformable mirror to add back the correct distances or
So-
delays.
Good. This is very interesting. I'm sorry, you're gonna
Does it make sense?
keep definitely, absolutely make perfect sense. Then I still bringing questions.
Sure.
Just keep. I have a question now. How do I know this? What's the right image? How do I know the correct image?
Oh, good question. Well,
There must be a reference somewhere, right?
yeah, it's what is the right image? Well, that can be a tough question. But for astronomy, if we take a kind of common, simple case, if you looked at a star, stars are typically very, very far from us. And so they look, well, they're not resolvable. That is, we can't necessarily distinguish features on them from where we are on Earth. So they look like what we call point sources. And if you ever look in a textbook for an image of the point source, you'll see that you'll see this pattern that doesn't look anything like a point. It doesn't actually. It looks like a kind of a how would you describe it? It's called the point spread function, the airy pattern. Some people call it the kernel function.
Okay, I see. I kind of understand what you mean.
But it doesn't look anything like an individual point. It looks like a wave pattern.
That's right. Yeah.
Right? There's points of where the light is interfered constructively
That's
and
right.
completely destructively, where there's zero intensity.
Oh, and then I can fit. It's basically fitting like kind of experimental theory to make some sense of my image, right?
Yeah, and so it's a wonderful example of the theory of the wave nature of light, where it's actually dominating our results. Because you want to look at a star, and what you're not going to see an individual point. You're going to see the consequences of the wave nature of light.
That's right. Yeah.
On your detector or in your image.
I mean, yeah, if you took one trace of this image in one direction, let's say x-axis,
Yeah.
and you have the magnitude plotted along that axis.
Right. So this is the magnitude,
Vector.
and x-axis, and you plot it
Yeah.
straight through it. It would kind of look like a peak here, and then it'd go to zero,
Yeah.
and then it'd come back up to some value
Which is
and down, and then so on and so on.
Some like Bessel function or
Like
any.
a first order does. And so, yeah. So if stars don't look anything like stars, and it must have been really confusing when people
Exactly.
first looked at that and they said,
I myself.
all I see is this weird pattern.
It's not, what is the star?
Right, I guess I give up. But then Huygens would have been like, no, that's the wave nature of light.
Yeah.
You did it right. You'd be like,
Using machine learning, I always ask this question. I also asked this question to Vanessa and asked it to Bruce, and I got nice answers. But I feel like you'll tell me more details about if I want to use machine learning or artificial intelligence
yeah,
for this kind of process.
sure.
How I'm going to implement that? I have a picture in my mind, but I don't think it's a really clear image, to be honest.
But do you know that we just last night implemented artificial intelligence
Seriously?
on our AO system?
Oh my God. So my prediction were correct.
yeah. Your prediction. Now, yeah, right. Yeah.
Absolutely.
So,
So tell me more.
How do you do it? It's rather straightforward, and we're not the first to do it. It was done by some researchers at the University of Arizona.
Oh.
In astronomy, we've recently done it for biology applications, which we can talk about in the lab. But I guess in its simplest form, what you're doing is you're training the computer to associate, distortions or phase values or phase patterns in the electric field,
Yeah.
and the associative point spread functions or images. And what that really counts to is saying, by building up a neural network for the computer, it can have the opportunity to figure out if I'm seeing this pattern in the phase values of the light,
Yeah.
then I should expect this kind of an image over here. And consequently, you can run that backwards. So what we did is we took 30,000 pairs of point spread functions or images,
Yeah.
and their corresponding phase values that we generated with a deformable mirror.
So that's called the training set.
This is the training set.
Yeah.
And we built a neural network
Cool.
with that training set, and it took about a little over 4.5 hours on a supercomputer here at Stanford. And
4.5 just to run one process.
for the 30,000 data set, yeah, it was like
Wow.
64 gigabytes of RAM and
4 hours, you said?
a little over 4.5 hours, yeah.
Wow.
But
So we have supercomputer here in Stanford.
yes, yeah, it's really nice.
So supercomputer, I think already mentioned to you this some time ago, but supercomputer, you can think of it as maybe 500 single PC all stacked and connected together to process this kind of simulation or calculation. So he had one algorithm run for more than 4 hours in this big supercomputer, and he can tell us the power of machine learning or artificial intelligence when even it's getting into his field. It was independent field, but now he's working with in his field. I have just last question about the machine learning.
Yeah.
So I know if you have more sets, it could be good and it could be bad at the same time.
Right.
Of a set of sets of variables, I mean.
Right.
And in your case, I believe there are so many, excuse me, many variables.
For the distortions?
For distortion, but you still can limit them into 2 or 3.
Yeah, we have some very, very bright people who have kind of pioneered the field of adaptive optics. And they have given us a lot of useful tools and ways of understanding and decomposing and thinking about the aberrations that are caused by the random perturbations in the atmosphere.
Yeah.
And so we, from theory and from experiment, from previous experiments, have we've done a pretty good job of characterizing ways of representing the atmospheric distortions or the turbulence.
Yeah.
With Fourier modes and what is called a Zernike modes, which are radial basis set, orthonormal and orthogonal to each other. There's other modes like Karman-Love modes, and there's those modal basis sets can fairly accurately describe a random processes or random phase disturbances. And so we can train we've trained our computer with those kinds of distortions, which is exactly what we are typically using for the controller, which is relaying the commands from the wavefront sensor, the signals from the wavefront sensor to the deformable mirror.
So I think I have a lot of questions, but I will stop here because we have to go back to the lab. He has to work and I have to work. But he's going to take us in a tour, quick tour in his lab and explain to us how he used, as I mentioned, adaptive optics. So let's first thank him for this quick.
Thank you for having me.
We really wanted to talk to him a lot, but he is busy, man. Really, trust me in this. Okay, we will see you in the lab soon. Welcome to Professor McIntosh, Bruce McIntosh lab. This is his lab. It's a part of his lab. He has like 2 labs, I think, or maybe 3. And Dr. Andrew working in this section here. So Dr. Andrew and his colleague built this very nice setup. He's going to explain to you in details what exactly this arrangement or this kind of optics, what he does with it. But before we go to the setup, I think he would like to tell you a little bit in more details about what he explained just a couple of minutes ago about the images and how what type of process he can do with that images. So, Dr. Andrew?
Sure. So if I can point your attention over here, this is an image that's captured with a CCD, actually with this system. But if you take an image through the atmosphere of a star, and you take it somewhere in the optical or near infrared wavelengths, and you just take a snapshot really fast, like a millisecond or something like that integration time, you will see a very, very similar form to the intensity as is shown here. So this is kind of a representation of a single snapshot through the atmosphere and what the turbulence does, because if you remember outside, a star shouldn't look anything like that. It should look like the point spread function, the Airy pattern. And the adaptive optic system will correct for that. So if we turn the AO system on here, it'll take this.
What's the AO system?
Sorry, the adaptive optic system.
Yeah.
If we turn the adaptive optic system on, which we do for correcting through the atmosphere, and in the lab here, then this kind of blurry pattern, this single snapshot, will essentially go away, and you'll have this kind of point of light here at the center, and you start to see this interference with these airy rings kind of spiraling out from the center. And that's very, very similar to what a star looks like once you've corrected for the atmosphere.
So this is after correction?
This is after correction with the adaptive optic system. So you had before with the aberration, a bunch of little spots. for a single snapshot, and then afterwards you have a kind of a crisp image with some area patterns around it. This one's not perfect. Ideally, this would be the area greens would be circular and perfectly symmetric. The system is not perfectly aligned right now.
And these just for alignment, or what exactly? Is this a part of the function of the transformation? Or?
It's this actually comes, the energy that you're seeing here, the light energy you're seeing at these points comes from a spatial frequency across the deformable mirror, and so that gets mapped out to these points here. I guess the point is, like, this is what a star looks like to a telescope within the AO system imaging in the optical or near infrared through the atmosphere. And this is also a representation of what we are using here in the lab. Of course, we don't have stars here, but we're using these particles that are nanoparticles. They're a few tens of nanometers in diameter. And when you excite these nanoparticles with a laser light, they will emit in the near IR and in the visible.
I think they might be a little bit lost when we talk now about nanoparticles. Yeah. So maybe
Why the particles?
Yeah. Why nanoparticles first, and
Yeah.
then how do you get the nanoparticles to come into this picture for a second point?
Yeah. So why the nanoparticles? So the nanoparticles.
What are nanoparticles? So, there are people here have no
yeah.
idea.
Nanoparticles are, well, if you're familiar with the prefix nano, we're just talking on the order of 10 to the minus 9 meters. So very, a billionth of a meter's length scale.
Yeah.
And these are very small, 10 nanometers.
Yeah.
And they are very small particles that have essentially have some rare earth elements in them, like neodymium and yttrium,
which can emit.
Which can emit in the near IR and in the visible wavelengths when they're excited with light. Does that make sense?
Yes, I think it makes sense. I will try to translate. Do you mind if I translate in Arabic?
Please.
So for the people who speak Arabic or the audience, هو يتكلم عن الجسيمات المنممة كما زي ما قلت من قبل. النانو بارتيكلز أو الجسيمات المنممة هاي هي حد نفسها قد تكون من المواد المشعة، بس مش مشعة غير ضارة، وبتكون خاملة إذا أنت استخدمتها من غير إشعاع. إذا قمت سلطت عليها إشعاع أو ليزر حتصبح مشعة. Sorry for that.
No need to apologize. Yeah.
I just explained how the mechanism excites the nanoparticles by shooting them with laser at some certain wavelengths and so on.
Okay, great.
Yeah.
And so those nanoparticles are going to act like stars in the sense that in astronomy, the astronomers want to look and study a star, but the light from the star also provides information to the adaptive optic system.
I see.
And in our case, this is the topic we were talking about with the collaboration with Professor Stephen Chu.
I see.
And so we've been working on an adaptive optic system for a biology application, where we're trying to image several millimeters in through tissue and trying to get optical resolution of nanoparticles and of cancer cells.
So this is the point where astrophysics or astronomy and medical or biology meets. That's the point. Instead of I see this, I call it a star. This will be my biological sample.
Yep.
Or
This will be your nanoparticle. Right.
I see.
And the nanoparticle, when it emits, the light that propagates out from the nanoparticle encounters the tissue in the sample. And the tissue or the skin or the different biological cells that it travels through all have varying index of refractions. And so again, just like the atmosphere, they impart delays of phase or delays of time or delays of distance into the light.
I see.
And so our initial images don't look anything like this. They look like what I showed you earlier, very distorted. Just like what we see if you look into the atmosphere.
So I have a problem now, a little problem. Or maybe I want to see if I understood this right.
Please.
Before we're dealing with an object which is really far away from us, and that wave traveling all that way, and when it reaches us, it's like the front is almost plane wave.
Right.
So what makes the nanoparticle wave front plane is attenuation through the tissues? or how, because the short distance now is we have very short distance.
It's a short distance on the order of like 3 millimeters, but that's still much larger compared to the wavelength of the light.
Single particle.
Yeah, which is like the wavelength of the
Oh,
light is like a micron, and the single particle is maybe 5 to 10 nanometers.
I wanted to ask you this question, but I forgot, and I think I should ask him now. You're someone with a background of electrical engineering. So, how did you find this transition from atomic from electrical engineering into physics?
But I think after enough time in a field or working with the general principles, if you have a good understanding of them, you can understand how they would be applicable or translated in other disciplines.
Okay.
Because, for example, Professor Steve Chu saw what Professor McIntosh was doing in astronomy, and thought, well, we could do that in biology.
Yeah, exactly.
And Professor Chu is a background Nobel Prize in physics and has been doing a lot of interesting research in biology lately. So there's nothing that says that you can't like learn the other field or take what you have as a knowledge base of a skill set that you've developed from your studies and use that in a slightly in a different field, even though we call it something else. But the underlying mechanical principles of nature are still the same, or typically the same. And if they're not, then you learn.
Okay, so now we can go to the, I think if you like, if you don't mind, we can go and check. If you want to add anything out here.
No, I hope that was clear.
I think it was clear. So there's, you mean explained very well. And, For me, it's very clear. I think if you have questions, you just post them and.
Yeah, and I'd be happy to answer them.
He might answer. I will answer, and I will try to translate to you if you like for the people who speak Arabic. Right.
So I guess just to add one more point around the nanoparticles. The nanoparticles will be essentially delivered inside of cancer cells and tumors, and they because they emit light, that lets us essentially measure the aberrations that are limiting our ability to resolve the features and study the samples and study the cancer cells. And these particles act very similarly to what we call reference beacons. And
what's a reference beacon?
A reference beacon, like I was talking about outside when I was mentioning laser guide star.
Oh, I see.
A reference beacon and laser guide star are the same, different names for the same thing. But they're essentially, small points of light that give you information about the index of refraction variations.
Oh, I see.
Or about the aberrations in the simple. And so in astronomy, in adaptive optics in astronomy, sometimes you don't want to look at a really bright star. Sometimes you want to look at the center of our Milky Way, at the black hole.
And then you just block that bright star, or.
Well, no. Say if you're looking at the black hole, there's no bright stars nearby, but you want to look at it in the optical and infrared. But it's the light coming from that region around the black hole is still going to be distorted when it goes to the atmosphere. So you have to find a way to put a beacon up there, or put a light source up there above the telescope, somewhere in the atmosphere, so you can illuminate the turbulence and see it and correct for it.
I see.
And so in astronomy, we do that with lasers, and we shoot a laser up through the atmosphere, and it's particularly tuned to the sodium atom, the D2 transition of the sodium atom, and that electron, that valence electron of the sodium atom, when it drops down from the excited state, it gives off a very nice orange-colored light. It's 589.2 nanometers, and that light from the sodium atoms, essentially, just like these nanoparticles, propagates through the turbulence, and that lets us see the turbulence or measure the turbulence and correct for it.
Is that what you describe now is a beacon, or?
That's the beacon.
Yeah,
So what you do is you shoot a laser up from the side of the telescope that you're observing with, and about 90 kilometers above us, there's a 10-kilometer thick layer of sodium atoms, and they're deposited there when meteorites burn up through the atmosphere. And so if you sight those sodium atoms, they will re-emit light, and that re-emitted light comes back down through the atmosphere through the telescope, and lets the adaptive optics system measure the turbulence when there's not a bright source near the science target you want to look at.
And then I can tell from the looking at the distance from the laser to the point where it reached, and then I can see the spectrum of the sodium, and just see how much attenuation I have at each point.
We don't use it for measuring the attenuation of different altitudes. It's really just to provide information about the distortions that are caused by the turbulence.
Oh yes, because the correction is not like this direction, correction is this direction, so you don't care too much about it.
Right. Yeah, you don't care about the z direction as much as you do x and y.
I see.
And so these nanoparticles act just like a beacon or the laser spot in the sodium layer, where the laser is going into this system and hitting the nanoparticles. The nanoparticles are emitting light, just like the reference beacon or the sodium laser guide star, and that light's coming out of the sample, out of the tissue and the cells, and it's picking up the aberrations, and that lets the adaptive optics system measure the turbulence and correct for it. And so that's what I was doing back in graduate school, was working on a sodium laser guide star adaptive optics experiment, and now working on this biology system.
Yeah. So I think we can now look at the experiment.
Yeah.
All right.
Yeah. So I just wanted to show everyone kind of a tour of the system here. This is our adaptive optics system for biology applications. The sample or the nanoparticles in the cells sit over here, and they'll be in a microscope objective, and that's going to pass. That's excited with a laser that passes through here, and then the light that's emitted from the particles is captured by this lens here and sent through the adaptive optics system. The main components of the adaptive optics system are the wavefront sensor that's located right here. And for some of those of you who are interested, this is a Shack-Hartman wavefront sensor. And then we also have this is the device, the deformable mirror, which is, correcting for the delays of phase, delays of distance by physically translating its surface. You can see the gold surface there of the device behind a window. And there's 32 by 32 actuators, 1,024 actuators arranged on a square grid. And these are ribbon cables that relay the high voltage drive commands to the deformable mirror, typically around 100 to 200 volts. And then the light from the particles pass through this entire system, through these relay lenses, and then over here to the cameras. We have just a simple CMOS camera for checking alignment, and then we have a really nice near-infrared camera for essentially imaging particle light from 800 nanometers to about 1.5 microns. So that's the system kind of overview.
Unfortunately, we reached the final moments with Dr. Andrew. I'm very, very glad that I managed to capture this guy and talk to him and learn a little bit about his experiment. I had no idea what he was doing, and now I'm very happy to hear him talking, explaining his research in detail. I would like to invite Dr. Andrew because I'm from Sudan. I'm very concerned about science in my country, and I'm trying my best to highlight research in Stanford, which is done by pioneer people, and bring it to people in Sudan to learn more about science and the variety of physics and what kind of experimental research we do here. So I'd like to invite him, as I said, to deliver or to tell the people in Sudan, the researchers in general, and the young people, the incoming researcher in particular, tell them his message or what he wished for them to do.
Well, I guess I hope you enjoy doing science and art. Art is also equally important too. I like them both. I like science a lot. I think research is important, especially at the university level, or I mean any level, but at least to me, university research kind of represents a place where the end goal is not to produce products. It's really just to try and learn more about the world around us.
Yeah.
And I think that's fun and exciting. It's also very challenging, to be honest. I find it really hard, but rewarding. And I think studying the sciences is good for individual development and for staying open to new ideas. And also for trying to, find new discoveries and help humanity in whatever way one could.
I know Sudan, and you probably know that Sudan has a lot of problems that range from politics to environment and poverty, and there could be like so many research. It doesn't have to be in this type of research to improve that situation or that environment, or to help people to get rid of the poverty or to bridge the gap between
Right.
Dr. Andrew and Ahmed from Sudan. But seriously, I think the solution for all what we have, not only in Sudan but in all third world, in Africa, or is that it can only overcome by science, educating people. So research is one key for people to learn about their own environment, because you might know that there are problems, but if you don't go and dig and do research, you will never know anything about your environment. So I think he has a point in this, Dr. Andrew. So, do you want to be a professor? It's a very bad question. You can skip. Sorry.
Sure.
But I would love to call him Professor Andrew, because
Maybe one day.
this person with this type of personality, he deserves to be. I see in him really a very successful professor, to be honest. So thank you again, Dr. Andrew.
Sure. Thank you for having me.
I'm very
Thank you
glad.
for having
I'm
me.
very glad you came and talked to us. And okay, guys, say goodbye for now, and let's look forward to another interview. And as we promised, if you have questions to him, just post them down in
Please,
the comments,
yeah.
and we will try to answer them.
Thank you.
Goodbye.
Previous experiments have we've done a pretty good job of characterizing ways of representing the atmospheric distortions or the turbulence, with Fourier modes and what is called a Zernike modes, which are radial basis set, orthonormal and orthogonal to each other. There's other modes like Karman-Love modes, and there's
The long ones.
No, not like that. Okay, no, come on. But they
Did you? Okay, this is the last question about this one. Then we go.
Does that answer your question?
Partially. Okay.
I might have missed
Not
it.
really. This time, not really. Maybe you can back it up with the answer for this question.
Okay.
So, welcome to Dr. Andrew's lab.
No, Professor McIntosh's lab.
Ah, this is Professor McIntosh lab.
Yeah.
Okay. Okay, welcome to Professor McIntosh, Bruce McIntosh lab. This is his lab, and as you know, Dr. Andrew, he works in his lab. So the setup behind me is the experiment which Dr. Andrew built by himself.
No, with some colleagues. Sorry. Okay, from the top. I didn't know.